Your brain's ability to resist temptation isn't about sheer willpower. Instead, it's deeply rooted in the prefrontal cortex, which governs decision-making and impulse control. A 2012 study by Stanford University showed that glucose, a simple sugar, fuels this brain region's activity. However, when glucose levels drop, your cognitive control weakens. This means that self-control isn't about moral strength but energy supply. This biological fact contradicts the common belief that willpower is solely a mental skill. The prefrontal cortex literally runs on fuel, and when it's depleted, your ability to resist temptation diminishes. It's less about character, more about chemistry. Stress is often seen as a test of willpower. Yet during stress, your brain releases cortisol, a hormone that disrupts the prefrontal cortex. This hormone enhances the amygdala's activity, the emotional center of your brain, leading to impulsive reactions. A 2015 study by Yale University found that elevated cortisol levels reduce gray matter within the prefrontal cortex. This structural change can impair decision-making and self-control. The myth of conquering stress with willpower ignores these cortical changes. Your brain's wiring shifts under stress, prioritizing survival over self-control. The tug-of-war isn't mental, but molecular. Habit formation is often misattributed to willpower alone. However, it's the basal ganglia, a cluster of neurons that encodes habits. The brain uses dopamine to reinforce these behaviors. A 2014 study from MIT showed that neuronal circuits in the basal ganglia strengthen with repetition, not force of will. Habits become automatic over time, bypassing the prefrontal cortex. Thus, willpower has limited influence on automatic behaviors once they're established. The encoding process isn't about motivation but neural circuitry. It's a rewiring, a shift from conscious effort to unconscious routine. When you rely solely on willpower, your brain's energy reserves deplete quickly. The anterior cingulate cortex, a region involved in error detection, also plays a role. A 2010 study by the University of Toronto found that fatigue reduces activity in this region, impairing self-control. This reduction affects your ability to monitor and adjust behavior. The myth of endless willpower ignores these neural energy constraints. You can't simply power through. Your brain requires recovery. This biological energy expenditure limits how long you can sustain self-control. It's a finite resource, not a boundless force. Believing willpower is infinite ignores the brain's neuroplasticity. Long-term stress alters your brain's structure, reinforcing negative habits. A 2013 study by King's College London demonstrated that chronic stress reduces synaptic connections in the prefrontal cortex. This reduction makes it harder for neurons to communicate, affecting your impulse control. The structural changes aren't just psychological, they're tangible. Your brain's adaptability works against you when stress persists. Over time, this rewiring undermines the myth of willpower as a remedy. The brain molds to its environment, often beyond conscious control. Cortisol, the stress hormone, affects your brain at the cellular level. It reduces dendrite density in the hippocampus, the memory center. This was highlighted in a 2016 study by the University of California, Berkeley. Fewer dendrites mean less synaptic connectivity, impairing memory and decision-making. The hippocampus is crucial for forming new memories and integrating information. When cortisol levels are high, these dendritic changes diminish your cognitive flexibility. The structural impact of cortisol isn't just temporary. It can have long-lasting effects on brain function. Stress alters neural architecture, reshaping how you process and respond to the world. The amygdala and prefrontal cortex have an intricate relationship, disrupted by stress. Stress enhances the amygdala's activity while suppressing the prefrontal cortex. A 2017 study from Harvard University used fMRI to show this altered connectivity. The amygdala signals emotional responses, while the prefrontal cortex manages rational decision-making. Under stress, this connection weakens, and the amygdala dominates. This shift prioritizes immediate emotional reactions over logical thought. The neural pathways between these regions reconfigure, reducing your control over emotional impulses. Stress doesn't just cloud judgment, it rewires the network governing emotion and reason. Long-term exposure to stress impacts dopamine receptor availability. Dopamine is crucial for reward and motivation pathways in the brain. A 2018 study by the National Institutes of Health found receptor downregulation in the nucleus accumbens. This area is critical for processing pleasure and motivation. With fewer dopamine receptors, the brain's reward system becomes less responsive. This dampened response makes it harder to feel satisfaction, driving compulsive behavior. The alteration of dopamine signaling under stress isn't just psychological, it's a tangible change in receptor density. Your brain's reward system shifts, affecting how you pursue goals and regulate behavior. Habits are encoded by the basal ganglia through repetition. Dopamine release during a habitual action strengthens synaptic connections. This process was detailed in a 2019 study at the University of Cambridge. The striatum, part of the basal ganglia, is where this encoding occurs. Over time, these reinforced pathways bypass conscious control, automating behavior. The basal ganglia's role is not about willpower, but about efficiency. Habitual actions are stored as neural pathways, reducing the cognitive load on the prefrontal cortex. Your brain optimizes for energy conservation, signaling that habits are deeply ingrained neural patterns. Stress impacts BDNF expression, a protein vital for neuroplasticity. Brain-derived neurotrophic factor supports neuron growth and synaptic plasticity. A 2020 study from Columbia University showed stress reduces BDNF levels in the prefrontal cortex. This reduction impairs the brain's ability to adapt and learn new behaviors. BDNF is crucial for forming new neural connections, enabling self-control and learning. When BDNF expression is lowered, your brain struggles to adjust to new challenges or resist old habits. The physiological impact on BDNF isn't a surface-level change, it's a core disruption. Stress alters the brain's capacity to adapt, affecting long-term behavior regulation. Chronic stress and acute stress have distinct effects on the brain. Acute stress can enhance cognitive performance temporarily by boosting adrenaline. However, chronic stress leads to sustained cortisol release, which damages the brain over time. A 2014 study from New York University showed chronic stress shrinks the prefrontal cortex, impairing decision-making. This structural change reduces neural plasticity, making it harder to break old habits or form new ones. Acute stress might prime your brain for action, but chronic stress erodes its structural integrity. The prolonged exposure isn't just taxing, it's transformative, reshaping your brain's architecture. The self-help industry often oversimplifies willpower, ignoring neuroscience. Claims that mental strength alone can overcome obstacles neglect the role of neural mechanisms. A 2019 meta-analysis in the journal Psychological Science found that interventions focusing on biology, not just psychology, yielded better outcomes. This analysis reviewed over 200 studies, showing that understanding brain chemistry is crucial for behavior change. The disconnect between popular psychology and neuroscience highlights a gap in self-help narratives. It's not just about mindset, it's about molecular and cellular processes that govern behavior. The brain's complexity defies simplistic self-control solutions. Brain imaging studies reveal the limits of self-control. Functional MRI shows that tasks requiring intense focus deplete prefrontal resources quickly. A 2013 study by the University of Michigan used brain scans to demonstrate this depletion. The scans showed reduced activity in the prefrontal cortex after prolonged cognitive tasks. This reduction compromises your ability to exert willpower. The myth of endless focus breaks down when viewed through the lens of energy consumption. Your brain operates on finite resources, and imaging studies make this vividly clear. Self-control isn't just a mental exercise but a physical one, with visible limits. Popular psychology often misinterprets the default mode network, DMN. This brain network, active during rest, is linked to self-referential thoughts and daydreaming. A 2016 study from the Max Planck Institute found that excessive DMN activity reduces focus. The more active the DMN, the harder it becomes to maintain task-oriented attention. This contradicts the idea that the mind can always be harnessed for productivity. The brain's default mode isn't easily overridden by willpower alone. Instead, it reflects a biological propensity for mental wandering, challenging the concept of constant self-discipline. Your brain naturally oscillates between focus and reflection, beyond sheer control. A 2021 study by the University of Oxford highlights a reframing fact: willpower is context-dependent. The study showed that participants who restructured their environment needed 60% less effort to exert self-control. This was observed in a sample size of 300 people over 6 months. The brain responds to environmental cues, modulating the effort required for self-regulation. This isn't advice. It's a shift in understanding how context influences neural processes. The external environment interacts with internal neural states, shaping behavior. Self-control is not just an inner struggle but an interplay between brain and context. Your surroundings can significantly alter your brain's demands for willpower.